Hi everyone, and welcome to the last part of this unit, which is integration of rational functions by partial fractions. So to start this particular section, we are going to do a review of integrals. And you'll see that many of the ones that we're doing as review here are going to involve the ln, or the natural log function. Some of them might involve some trig, but mainly the natural log, which we will be using in this particular lesson. In addition, we're going to do a review of long division. So hopefully you can think back to your algebra days and remember a bit about long division. I'm going to do this review very quickly and not exactly show every step since this is review. So my suggestion for how to work through this would be to pause the video and answer the questions, come back and check your work. So I have the first three done, except for the last one, which is nearly done. I'm going to quickly talk through them. This first question is pretty much the definition of the antiderivative of 1 over x. And that's something you had to memorize a while ago, which was the natural log of the absolute value of x plus c. So hopefully you remember the first one. The second one, you would have needed to do a small u substitution, with u being x minus 2, and then taking the derivative of u, which gave us du, taking the derivative of x minus 2, which is just 1 dx, or just dx, replacing all of those x terms in terms of u in our integral, which would give us the integral of 1 over u du, taking the antiderivative, which would be the ln of the absolute value of u, and then replacing u with x, and don't forget your plus c. For this last one here, it's very similar to the second one. However, in this one, it did have a coefficient here when we were taking our derivatives. So we had the derivative of u is du, the derivative of 3x plus 2 is 3 dx, and then we would have to solve for dx, and that would be 1/3 du. So what we'll do at this time, I like to take that 1/3 and put it in front, and then just rewrite this as 1 over u du. That 1/3 just carries down to the ln of the absolute value of u. And then, of course, replace at the end your u with whatever you set it equal to in the beginning, which in this case is 3x plus 2. And don't forget your plus c. So those are the first three. So I'd like you to take a moment and work on the next three. Okay, so what we have in this first one, our u would be 3x plus 2, the derivative would be 3 dx, and you'd solve for dx, giving you 1/3 du. Putting that 1/3 out in front, you'd have 1 over u squared du. That u squared can be brought up as u to the negative 2. When you add 1 to negative 2, you get negative 1, so you're basically dividing by a negative 1 and multiplying by a negative 1. So that would be coming negative 1/3 in front, and then the u can go back down to the denominator. Then you can replace u with what u is equal to, which is 3x plus 2, and then you can distribute the terms in the denominator to get a final answer of negative 1 over 9x plus 6, and then plus c. For the second one we have here, we have our u value as 2x squared plus 2. The derivative would be 4x dx. Notice in this example, we have an x and we have a dx, so we only needed to solve for x dx by moving over the 4. So we would have an integral of 1 over 4, putting that coefficient out in front, of the integral of 1 over u du. That's 1/4 ln of the absolute value of u. Replace what u is equal to with its x terms. And then notice what's inside the absolute values here would never be equal to 0. So you don't need the absolute values, and you can put parentheses. Don't forget your plus c. So in this last one, it's not going to be a u substitution. Notice it has a constant up top. So this 1 here is a constant. And this bottom here is a quadratic. So we should notice that this kind of takes the form of something that we're familiar with. Something that you might be familiar with is that the integral of 1 over x squared plus 1 dx is equal to inverse tan or arctan of x, of course, plus c, once you get your final answer. So this is something you might remember from a while back, and hopefully we can use that. Notice this is almost in this form, except this 3 in our original question here is there instead of a plus 1. So we need to try and figure out a way to manipulate this integral to get it to look like this. So my first thought is that I need to get this 3 to a 1, and I can do that through division. But I can't just divide the 3. I have to divide everything in the denominator by 3. And if I divide everything in the denominator by 3, I need to make sure that I'm really not changing the meaning of the equation or the expression here, the function. So I also need to multiply by a 3 so that I'm really just manipulating it with a 1. So here's the idea. Let's take the function here, and I'll rewrite it. And we're going to go 1 over x squared plus 3. And if I divide everything by 3, I also need to counteract it with that multiplication piece that I was talking about. Okay, so I can rewrite that as, and remember we're taking the integral of this, so I need to put that dx before my equal sign. Okay, so dx there equals, and I'm going to rewrite that as 1 over 3 parentheses, and then what I really have here is x squared divided by 3 plus 1. Now, that 3 in the denominator can come out as a 1/3 in front. So I'll do that. And I'm going to also make this term here the same meaning but a different way of expressing it. So I'm going to take the 3 and put it on the inside of that square. So I'm going to make it a cube, or a square root of 3, a square root of 3, because the square root of 3 squared is actually just a 3. So that's what I'm going to do in this denominator here. So it's going to be x over the square root of 3 squared plus 1. And this is allowed because in this piece up here, this x squared in our general form of the inverse tan here, this really is just saying whatever this term is in front, it's just squared. So now we have whatever that term is being squared and adding 1. And so now this is in the term of, or this is in the way a inverse tan integral would be written. So we can go ahead and take that. So it's going to be 1/3 in front times, this is just going to be inverse tan, or arctan if you prefer to call it that. And then instead of being in terms of x, it's going to be in terms of, so up here we have terms in terms of x because this is just an x. But now, instead of being in terms of x, it's going to be in terms of x over root 3. So we're going to put that x over root 3 in there. And then we don't want to forget our plus c. So that's our answer to the bottom 3 for the review of integrals. Hopefully these helped a bit because these ideas will come into play later. Now let's talk about the review of long division. So think back to your algebra days when you were doing long division with polynomials. And maybe you'll remember that a fraction or a rational function with polynomials simply means the top, the numerator, is being divided by the denominator. So the numerator polynomial is being divided by the denominator polynomial. So I'm going to write a division bar here. The only trick with long division is you have to make sure that you have a term representing each of the degrees of the polynomial. So this top polynomial is 3 degree, and then so our exponent is a 3, a 2, a 1, and then our constant would be a 0. So that is all represented okay. So I'm going to go ahead and put that inside the division bar because that's what's being divided. Okay, and then the bottom is what we're dividing by, so this is our divisor. And notice it has an x squared term and it has a constant term, but it doesn't have a linear term. So we are going to go ahead and write that in there, but with a 0. So it's kind of like our placeholder. Okay, so now we have everything represented. The next step is just going to be like when you did long division with just plain numbers. We are going to say, okay, well, in here I have an x cubed. My leading term here is x squared. So x squared times what gives me x cubed, and that's going to be an x. So then I'll take this x and so this x right here that I just determined, and I'm going to multiply with each of the guys in my divisor. So x squared times x is x cubed. X times 0x is 0x squared, and x times 1 is x. All right, now just like with division, you're going to subtract them. So x cubed minus x cubed should cancel. Negative 2x squared minus 0x squared would be negative 2x squared. And 2x minus an x would be just an x. And then remember to bring down your next term. So this should feel very much like something you've done before. So now we're going to say, okay, well, here's my divisor. What do I need to multiply my leading term of my divisor by in order to get this front term here, which is negative 2x squared? And so I would need to multiply by negative 2. So I'm going to go ahead and put a negative 2 up here, and then take that negative 2 and multiply it by each of the items in our divisor. So it's going to be a negative 2x squared plus 0x minus 2. Okay, so now I'm going to subtract again. Just be careful of your double negatives as you're doing this. So negative 2x squared minus negative 2x squared, well, that would actually cancel. And that's what you want to happen, right? X minus 0x is just x. And negative 2 minus a negative 2 is 0. So my remainder here is really just an x. And whenever you have a remainder, remember you always have to write it over top of your divisor. Remember our divisor is what we're dividing by, in this case x squared plus 0x plus 1. And instead of writing x squared plus 0x plus 1, I'm just going to write x squared plus 1 because the 0x isn't truly necessary unless I'm just doing a long division process. So this expression here, this x minus 2 plus x divided by x squared plus 1, this is equivalent to what we started with, okay? So let me just write a couple notes on there. So the little notes that I wrote is just, what the divisor is, what the remainder is, and how you get this lovely expression here at the end of our answer. So x minus 2 plus this new rational piece here. So what I said was that this beginning expression here, this beginning rational function, is the equivalent of what we just found, which is x minus 2 plus x divided by x squared plus 1. So those two are equivalent. So my question for us now is, what if I had originally asked us to take the integral of this rational function here? What if I had originally asked us to do this? We wouldn't have been able to do it when it was in this form, when it was pre-simplification, because it's just too complicated. So long division is one way of helping you simplify the rational function so that then you're able to take the integral of something. So this is one thing that definitely you want to keep in your back pocket as a way to help you integrate some of these difficult rational functions. So using long division, the key on that is you want to use long division when your rational function has a degree on top greater than or equal to the degree on the bottom. So when that happens, long division is the way to go. And that is what we had here to start with. We had a degree in our numerator, so the degree here was 3, that was larger than the degree in our denominator. So we approached this with long division, simplified the way it was written, and now we can actually take the antiderivative. And so what we're going to do is we're going to break this up into separate integrals. So I'll do maybe integral of x dx minus the integral of 2 dx plus the integral of x over x squared plus 1 dx. And now I can take the integral of each of these separately. Notice this third integral, however, we are going to need to still use u substitution to help us get through some of the nitty-gritty there. So I'm going to take a moment and set my u equal to the denominator. So my u would be x squared plus 1. The derivative of that would be 2x dx. Notice we have an x and a dx already in our integrand. So we're just going to move that 2 over with it becoming a 1/2 on the other side. So now I'm going to be able to rewrite this integral as the integral of, with a 1/2 in front, 1 over u du. And the antiderivative of that, of course, is the ln of the absolute value of u. Now, I don't want to forget about these guys up here that I have yet to actually take the antiderivative of, but they're very simple. So the antiderivative of x squared is 1/2 x squared, sorry, the antiderivative of x is 1/2 x squared. The antiderivative of 2 would be 2x, and so now we just need to combine forces here. Now this was a plus sign in between them. We're almost there. We just need to take this u expression in our ln and put it back in terms of x. So here I go. 1/2 x squared minus 2x plus 1/2 the natural log of, and I'm actually going to change this from an absolute value to a parenthesis. And the reason is because x squared plus 1 is always going to be positive anyway. So the absolute value isn't truly needed. So there's our answer, and our answer is lovely, but it was much easier to do when we did long division. Okay, so that's one of the approaches when you have rational functions. Now, as I mentioned before, we are going to be dealing with some rational functions here. So we're dealing with expressions on the top and expressions on the bottom. And the next method we're going to learn is called partial fractions. And so we're going to call the rational expression on the top here the px. So our function of top is going to be called px, and our function on the bottom is going to be qx. So together they make this lovely rational function, and we're going to be comparing their degrees. Now, the first one we already actually did an example of, and that was when your function on top is greater than the function on the bottom in terms of the degree, and that's when you use long division, okay? And that's what we actually did in our prior example. Okay, then we need to think about, well, that's always going to happen. What happens if the degree of px is less than the degree of qx? Then we need to go to steps 3 and 4. And so this is going to be dealing with what they call partial fractions. So what does partial fractions mean? Partial fractions basically is going to take these really complex functions that have like polynomial expressions in both the numerator and the denominator and break them down into more simplified fractions that you can then take the antiderivative of. Well, where did they get this idea from? Well, here's the general gist of why. Remember back in algebra when you had maybe a larger function on the right and two smaller pieces on the left, and they would say, okay, prove to me that these two are equal. And you would say, okay, well, this one on the right has a common denominator, whereas this one on the left does not. What if I were to try to get this one on the left to have a common denominator? So what you would do is you would multiply the first piece by the denominator of the second fraction here. So you do that in both the numerator and the denominator. And you do the same idea with the second piece here. You would multiply it by the denominator of the first little fraction. So it would be multiplied by x minus 1 in both the numerator and the denominator. Then you would distribute the 2 upstairs here. You distribute your negative 1 upstairs here, and you get 2x plus 4 minus x plus 1. And then our denominator would be common. It would be the factors x minus 1 and x plus 2, which is what I have here. Now, if I simplify the numerator, that gives me x plus 5. And if I simplify the denominator, that actually expands this, it would be x squared plus x minus 2. And isn't that what we started with? So notice these two expressions that we have here, one when it's expanded on the right, and the other when it's written in little pieces and fractions on the left, they are actually equal. So what we're going to be doing is we're going to be going from something maybe that looks like what's here on the right and breaking it up into pieces, which is what you'll have here on the left. So that's what we're going to be doing. So let's do it. In this case 1, this is an example of when you are going to have the denominator q of x is a product of distinct linear factors. That means no factor is repeated. Okay, so let's see what this would look like. Well, currently my denominator is not in any factored form at all. So I'm going to take a moment and factor the denominator. So I was able to take the denominator and factor it into two factors, 2x minus 3 and x plus 2. So this original function here can be rewritten. Our numerator, notice, is staying the same, so I haven't done anything with that. But my denominator can now be written in these factors. And notice that these factors are linear, right? Their degree is a 1. 2x minus 3 has an exponent of a 1, so that's a linear factor, and so is this x plus 2. So because they're distinct linear factors, distinct meaning nothing is being repeated, they're each unique, we are going to do case 1. Now that we've rewritten this expression, we're going to go up here and look at our directions, and it says that when you're dealing with linear factors, you're going to express it using a over one of your linear factors, b over your other linear factor, and then however many linear factors you have would be how you would break it up. So we're going to write this as our first linear factor, 2x minus 3, and add that to our second linear factor, which is x plus 2. And the reason you're just putting an a and a b up here is you're going 1 degree less than the denominator. So if my denominator is linear, that's a degree 1. So a is just a constant, so that's degree 0, and same with b. Okay, so when you're dealing with linear factors, it's just going to be an a and a b. All right, so now let's do some manipulation. All right, so we basically have this expression here on the left, and it's set equal to this expression here on the right. And one of the ways I'm going to simplify this is take the denominator that's on the left and multiply by it. So I'm going to be multiplying by 2x minus 3 and x plus 2. And if I multiply on the left, I need to make sure to multiply on the right. So 2x minus 3, x plus 2 on the right. Now, because I'm multiplying on both sides, the denominator on the left will cancel, right? Because they have a 2x minus 3 here and a 2x minus 3 here and an x plus 2 here and an x plus 2 here. So that would cancel, leaving me simply with the expression 4x minus 13 on the left. Now, on the right-hand side, I'm going to do this first example really step by step so that you see why things cancel and whatever, but we're basically going to be taking each of these factors, so each of these guys here, and they're going to have to go in to each of the fractions in our brackets. So let's see what that would look like. So what I did here is I took this 2x minus 3 factor and x plus 2 factor and multiplied it to both little mini fractions here. So I multiplied it with the a fraction, which gave us a times 2x minus 3 times x plus 2 over the denominator, plus, and then I multiplied it with the b fraction, which gave us the same general setup. Now, if you notice, you're going to have some cancellation. So we are going to be canceling the 2x minus 3 here with its denominator and the x plus 2 in the second part with its denominator. Meaning what we have left is simply a times x plus 2 plus b times 2x minus 3. Now my left-hand side hasn't changed, so I'm just going to go ahead and rewrite that. And I want to talk about what we have in this expression here. So notice when you do this little distribution that we just did, what you're going to end up with is the denominator canceling, and that numerator is going to pair up with the opposite factor. So the 2x minus 3 term here would cancel with this little guy, and you get the a with the opposite factor, x plus 2. And then same general idea with this b. So the x plus 2 term in the denominator would cancel with its numerator, leaving you with just the b and the 2x minus 3 factor. So you can kind of do that general simplification and kind of leave that step out in the future if you'd like to. But I did want to show you why that works. Okay, so now we're going to take a moment and distribute the a and the b, and then combine some like terms. Okay, so when I distribute this, I'm going to get a times x. So a times x plus 2 times a plus 2 times b times x minus 3 times b. And then you need to kind of group together those that are the same. So you have x terms and then plain constant terms. Your plain constant terms are the ones with just the a's and the b's and no variable x with it. So we are going to have here the ax plus 2bx together, and then plus the 2a and the negative 3b together. Now, we can factor out a little x here and just have this as the coefficient a plus 2b, since they're essentially like terms. And we have the 2a minus 3b, which is just going to be our constant. And we're still equal to 4x minus 13. Now, what we're saying here is that this little polynomial on the left, this little linear polynomial, 4x minus 13, is equal to this funky looking polynomial here on the right. Well, notice on the left we have a linear term, 4x, and on the right we also have a linear term, a plus 2bx. And on the left we have a constant term, negative 13, and on the right we also have a constant term, which is 2x minus 3b. So we're going to set the linear terms equal to each other and the constant terms equal to each other to see if we're able to determine what our a and b values are. So the linear term I have here in pink, so I take its coefficient, a plus 2b, and set it equal to the coefficient of our x term, the linear term here. So 4 is equal to a plus 2b. Same idea for the constant. We set the constant term equal to the constant, so negative 13 is equal to 2a minus 3b. So now if you notice what we have here is a little systems of equations, and we're going to go ahead and solve that. So what I did is I'm trying to get my a terms to be the same number opposite signs, so I multiply that top equation by negative 2 all the way through, which gives us negative 8 equals negative 2a minus 4b. And then now that they are the same number opposite signs, I'm going to add my equations together, and I'll get negative 21 is equal to negative 7b, which is telling us that b is equal to 3. And now that I know that b is equal to 3, I can figure out what a is equal to. So I'm going to take, I think the easier equation is this 4 equation. So 4 equals a plus 2 times 3. And of course, that's 4 is equal to a plus 6. So that's telling us that a is equal to negative 2. So now, kind of taking these two numbers, a is negative 2 and b is 3, we're going to go back up into this partial fractions here and replace the a with what it's equal to, which is negative 2, and the b with what it's equal to, which is 3, and we will have decomposed this initial rational function into partial fractions. And so our final answer would be negative 2 in place of a over 2x minus 3 plus 3 in place of b over x plus 2. So these two functions are equivalent. All right, let's look at case 2. So case 2 is when your denominator is a product of linear factors where some of them are repeated. And notice in our denominator here, this initial factor is by itself, it's unique, but this second factor here is repeated because it has an exponent of a 2. So to get this set up, the left-hand side stays the same, but the right-hand side, remember, has to be expressed as several fractions, right? And your denominators are going to be your linear factors. So we have a 2x minus 1 fraction, and then we'll have our x minus 2 fraction, and that's going to be to the first power. And whenever you have one of the repeating ones, in this case we have an x to the second, you have to write it basically twice with increasing powers. So you write it with a first power, and then you would, so here's our first power one, and then here's our second power. So if it were a cubed, we would write another one with the third power. So you just kind of write a fraction continuously until you get up to the degree of what's in the original denominator. Okay, now each of these numerators, because each of the factors is linear, so 2x minus 1 is linear, x minus 2 is linear, and x minus 2, the actual factor, is linear. We know it has the square here, but the actual factor here is linear. We're just going to write our a, b, and c. Now, to get rid of the denominator, we're going to basically, as we did before, multiply through on both sides by what's in the denominator, so it would cancel on the left, and I didn't actually write them in there, but I'm assuming you know that we're multiplying through by those denominators, and I will do the same on this side, so 2x minus 1 and x minus 2 squared. Okay. So now we have to distribute through, and instead of actually doing all the steps, I'm going to kind of do some simplifying as we go. So it's going to be a times, now notice this 2x minus 1 here is in the denominator already, so I don't need to bring over the 2x minus 1, I just need to bring over the x minus 2 squared. So that's what I'm going to do. So x minus 2 squared, because if I were to bring over the 2x minus 1, it would just cancel anyway. So I'm just kind of saving myself the step. All right, so then I'll have b times, and our denominator here is x minus 2, so I need the 2x minus 1s, and I only need one of the x minus 2s, because there's 2, and I already have 1, so I only need one more. So this one's going to have a 2x minus 1 and an x minus 2, and then plus our c, which notice this already has the x minus 2 squared, so this whole piece is okay. We're just going to need to multiply by 2x minus 1. So it's going to be c times 2x minus 1. And again, the left-hand side, we just cancel that denominator out when we multiply through, so it's just going to stay whatever the numerator is. You just write it on the left. Okay, so instead of actually expanding all of this out, there's a shortcut that I'm going to show you, and it's going to use these little factors here to help us find very useful values for. So the idea is to leave your right-hand side in factored form, and you're going to pick values to plug into x for the entire equation. And the values that you choose are going to be x values that make your factors equal to 0. So looking at this first factor here, for example, x minus 2, the number that I would plug into this to get this factor equal to 0 would be 2, because 2 minus 2 is 0. So now that I know I'm going to have x equals 2, I'm going to plug a 2 into every x value in this long equation. So it's going to be 7 times 2 squared minus 29 times 2 plus 24. Now that'll get us the left-hand side. And then the right-hand side would be a times, and if I plug a 2 in, 2 minus 2 is 0. In this first factor here, 2 minus 2 is 0, so it's going to be a times 0 squared plus b times, and if I plug a 2 into this factor, 2 times 2 is 4, minus 1 is 3. So I'll put a 3 there, times, and then there's another factor I have to plug it into. 2 minus 2 would be 0. So this factor would be 0. Plus c times, and again, plugging a 2 in here, 2 times 2 minus 1 is 3. So c times 3. So notice what this does. It actually is going to cancel out a lot of your terms and leave it so that you have one variable left to solve. So this is a nice little shortcut. So this entire left-hand side, if I were to actually take the time and simplify that, it's going to equal -6. And this right-hand side, anything with a 0 multiplying goes to 0. So a times 0 squared is 0. B times 3 times 0 equals 0. So really what I'm left with is just 3 times c. And that's telling me that c is equal to -2. So instead of having to do systems of equations on this one, you can definitely do a shortcut. Now let's use the other factor to figure out what we should let x equal to maybe help us figure out another one of the a, b, and c values. So the second factor that we have here is 2x minus 1. So if I set that equal to 0 and solve for x, it will let us know what x value we should use. So if I let x equal 1/2, that would give me this factor equal to 0, because 2 times 1/2 is 1, and then 1 minus 1 equals 0. So if I let x equal 1/2, I'm going to plug 1/2 into each of the x's in the equation, and hopefully it will help us figure out another one of the variables a, b, or c. Okay, so I plugged 1/2 in for each of the x's, and in the factor pieces, I of course simplified. So for example, 1/2 minus 2 is the -3/2, so that's where these numbers are coming from. And then I would simplify the entire left-hand side, and that would give us the value 45/4, and that's going to equal the right-hand side. Now notice this b is multiplying by a 0, and the c is multiplying by a 0, so really all I have here is 9/4 a. So I would divide, of course, by 9/4, and that would give me an a value of 5. So now I know my a and c value, and it should help me figure out my b value. So now that I know a is equal to 5 and c is equal to -2, I'm going to let a equals 5 and c equals -2 in my equation, and I'm going to choose any x value that I want. And I would suggest choosing something like 0, because it's simple to work with zeros. And again, this is being randomly chosen, so you can choose an easy number that works for you. I would suggest 0. It works nice. So, or at least in this particular question. So we have these values that we're going to plug into our original equation up here, and then we'll simplify. So in my original equation, this x on the left and this x on the left are going to be plugged in with zeros. And on the right-hand side, the a will be replaced with a 5. All of the x's are replaced with zeros, and of course I simplified them. So for example, 0 minus 2 squared would be just negative 2 squared. B is what we're still trying to find, so that's a variable still. And then I just continued plugging in the known values. So now I'm going to simplify, and on the left-hand side, that would simplify to give us 24. And on the right-hand side, we would get 20 plus 2b plus 2. And if I were to solve that for b would equal 1. So now that I know all of the a, b, and c values, I can go back up to the original partial fractions and replace the a, b, and the c values with what we found. So in this question, our answer is going to be, and I'll have to squeeze it down here, we have 5 over the first fraction's denominator, which is 2x minus 1, plus our b value of 1 over our second fraction's denominator, which is x minus 2. And then our third fraction's denominator, or number, was negative 2. So negative 2 over x minus 2 squared. So now we have our answer for our partial fractions. Okay, case 3, which is the last case we'll do on this video, is when q of x, or your denominator, contains irreducible quadratic factors, none of which are repeated. Okay, so you won't have any of those exponents like 2 or 3 on your factors. So the first thing we need to do is look at our rational function and specifically evaluate the denominator and think, okay, how can I factor this? It's not going to factor fully, but let's see what I can do to make it a little more simple. Okay, so it took me just a moment, but I factored out an x because both terms had an x. So my factored denominator would be x times the quadratic factor, x squared plus 3. And so I rewrote my expression here with a new denominator. And because we're dealing with quadratic factors as well as linear factors, so let me go ahead and label that. Notice this first one, x, is a linear factor, whereas this second factor here is a quadratic factor. So far, we've only dealt with linear. And because we're dealing with quadratic factors, we're going to have to go back up to our directions to say, okay, how do I set up that partial fraction? So our directions say that when you have a quadratic factor in the denominator of your partial fraction, your numerator, once again, is going to be 1 less degree. So quadratic has a degree of 2. So our numerator is going to be a linear expression, ax plus b or cx plus d, depending upon what variables you have available. So you should see a linear expression up top, and it's because it's 1 degree less than the quadratic factor. So knowing this, I'm going to take my numerator and ignore it for just a moment because we're going to break it into partial fractions and set up my denominators. And my denominators are going to be the two fractions, one of which is linear, the other is a quadratic. And then I need to remember that my numerator for a linear term is 1 degree less. That's just going to be an a. And then what we just determined for a quadratic, it'll be a linear numerator. And in this case, it'd be bx plus c, because a was already taken. So now we have our partial fractions set up, and we need to try to simplify them so that we can start to figure out what a, b, and c are going to equal to. And the process from here on out is very much the same. You're going to take your left-hand side and multiply it by your factors that you have in the denominator, which notice are the same factors that you have here in the denominator of your partial fractions, right? So they'll cancel on the left. right? So the x would cancel with the x, the quadratic term would cancel with the quadratic factor. And then we're also going to multiply on the right, because what you do to one side, you must do to the other. So we're going to multiply by our factor x and our quadratic factor x squared plus 3. Okay. So again, I suggest using the idea, the simplifying idea while you multiply. So as I'm distributing through the denominator, or these two factors, to each of my fractions here, just remember that when I distribute through, the x term here would cancel with the denominator. So what I would really have is the resulting a times the other factor, which is x squared plus 3. So that x factor would cancel with this denominator. And then same for the second fraction. My bx plus c would multiply with both of these factors. The quadratic factor in this case would cancel, really leaving just the x for the numerator to multiply with. Okay, so now that I've distributed over here on the right, I still need to set it equal to the numerator on the left. So now I have this equation here, and I need to distribute the a through, distribute the x through. So basically distribute and combine like terms on the right-hand side so that I'm able to solve for a, b, and c. So I did just as I said. I distributed the a through this parentheses, and I distributed the x through the parentheses, and that gave me ax squared plus 3a plus bx squared plus cx. And then all I did was bring the two x squareds next to each other because they're like terms. And then since that's quadratic terms, I did the linear term next and then my constant term last. And so remember, when you have two of the same term type, in this case we have two x squared terms, I can factor out an x squared for those two and write their coefficients together. So a plus b, and then the x squared plus cx plus 3a. And again, that's equal to our left-hand side. So now that I have all of these set up, I'm going to look at their coefficients to help me solve for a, b, and c. So for the quadratic term, I see that I have an x squared on the left and an a plus bx squared on the right. For the linear term, I have a negative x and a cx. And for the constant term, I have a 6 and a 3a. So I'm going to take a moment and make little mini equations with their coefficients. So now that I've created these little mini equations, I can see that one of my variables, in this case c, is actually already given to me. So c is equal to negative 1. Then if I look at this pink equation, 6 equals 3a, I can see that that's very simple to solve. I just need to divide both sides by 3. So this is telling me that a is equal to 2. So now I know that a is equal to 2. And now that I know that a is equal to 2, I can plug that into this equation over here to help me solve for b. And 2 plus something equals b, so this is telling me that my b value is equal to negative 1. So I now have solved for each of the variables a, b, and c, and I can take these values and plug them back into the partial fraction that I had from the very beginning. So I took the a value of 2 and replaced that in the first fraction, and I took the b value of negative 1 and the c value of negative 1 and replaced it in the second fraction to give us our final answer here. Now we're going to start looking at the actual examples of taking antiderivatives of these rational functions. And luckily for us, we've done all of the hard work for the integrals. So example 1 corresponds to case 1. And I actually cut and paste the answer from case 1, which is the decomposition of this function here using partial fractions, so that I can go straight from this really challenging antiderivative to what we already decomposed it into, these partial fractions because these two expressions here are equal. So I'm going to go ahead and take this integral here and set it equal to these partial fractions. And this is actually something we already did, like I said, so we're not skipping any steps. You'll just have to look back at case 1 to see where these came from. Okay, so now I have the integral broken into our partial fractions, and I will need to break these into separate integrals because I'll need to do a little bit of u substitution on each of them. So negative 2 over 2x minus 3 dx, and then I'll also need to do the second integral, 3 over x plus 2 dx. Now that I have those broken into separate ones, I'm going to do a little u substitution. So I'll do u substitution on the first one. And actually, before I do u substitution on the first one, I erased the numerator because I'm going to pop that negative 2 out in front and make that a 1. And I'll pop this 3 out in front, the coefficients, and make that a 1. That'll make my u substitutions that much easier. So now that I have this set up and ready to go, in the first integral, I'm going to have my u be 2x minus 3, which would mean my du is 2 dx. And I don't have a 2 obviously up there, so I'm going to move that over to the other side with a 1/2. So 1/2 du is equal to dx. Okay, so I can actually rewrite this little integral we have right here as negative 2, and I like to put that 1/2 out in front, parentheses 1 over u du. Okay, now on the other one, my u, and because I've already used u, I think I'm going to use w. So w is equal to x plus 2. dw is equal to 1 dx, or just dx. So this one's a nice easy one. I'm going to rewrite this integral as plus 3 for our coefficient there, and then 1 over w dw. Okay, so now I just have to take the antiderivatives and we will be set and ready to go. So let's scroll down a little bit so I have some room. Okay, so this first one is going to become, well, negative 2 times 1/2 is negative 1. And then 1 over u, the antiderivative of that is the ln of the absolute value of u. And then the antiderivative of this one over here would be 3 ln of the absolute value of w. So now let's replace these u's and w's with what they're equal to, and then we should be able to get a final answer here. So we should have negative ln of the absolute value of 2x minus 3 plus 3 times the ln of the absolute value of x plus 2. And then because these were undefined, we do need to have that plus c there. So our answer is right here for us. So it wasn't too bad of an integral to do once we did the partial fraction piece, which is what we did in case 1. So when you see something like this, you'll have to many times do partial fractions first, which is a whole process, as you now know, and then once you get those partial fractions, take the antiderivative. Okay, so what we're going to do is jump to example 3. And example 3 lines up with case 3. And again, I kind of cut our answer from case 3 and put it here so that we'd have it to reference. So our integral is what we started with in case 3, which is this lovely rational function here. And then we are going to make it into partial fractions using our answer from case 3 above. So our partial fractions are going to be 2 over x plus negative 1x minus 1 over x squared plus 3. Now, this 2 over x here is fine. That looks pretty easy to take the antiderivative of. But this little guy here is still kind of funky, so we have to do something a little extra on it. And what we're going to do is we are going to break it into, so let me write this out, we are going to break it up into separate fractions, okay, and they'd have the same denominator, right? But separate fractions, same denominator, okay, with like denominators. So in essence, we're kind of just taking apart the numerator, okay? So this is going to now look like the following. So we'll have the integral of 2 over x as its own little integral, right? And then plus, and I'll write it together first, and then I'll separate the integrals in just a second. So we're going to write negative x over x squared plus 3 and a minus 1 over x squared plus 3. So as you can see, we literally just kind of took this first piece here and put it in the numerator, and then we did the second one and put it in the numerator, okay? And they still have the same denominator. So we could, if we wanted to, put them back together, but we don't want to because that makes our integral difficult to take. So I'm going to take a moment and write these as 2 separate integrals. Okay, so I have now separated these. I took the negative in front of this x and put it in front, and I put this negative in between these 2 integrals. So now we have our integrals all set up and ready to go. This first one is straightforward. The second one, we're going to have to use a little u substitution. And this third one should look familiar from the warm-up we did at the very, very beginning, where we did something with inverse trig, and particularly arctan. Okay, so let's see if I can set up my u's and get this rolling. Okay, so this first integral, I just popped out the 2 in front, and it's just 2 integral of 1 over x dx, which is one that we know. The second one did require a little u substitution, so u would be the denominator. The derivative of that is 2x dx. We have the x, we have the dx, so the 2 can move over to the other side. So when I rewrote my integral, I put that 1/2 in front. I brought down that negative sign as well. So negative 1/2, the antiderivative of 1 over u du. And then this third one should look familiar, like I said. It is of the form for our arctan, okay? And so we need to do a little bit of that manipulation again, and so I'll run through it one more time. Remember what we did before is we took the denominator and we divided the entire denominator by 3 so that that 3 at the end will become a 1. And when you divide by 3, you got to multiply by 3 so that you're not really changing the meaning of the equation. Okay, so, or of the expression, I guess. So now we would have this expression. We would have our integral from of 1 over, the 3 can be on the outside, the x squared over 3 plus 1. And then we would be able to take this 3, pop it out in front as a 1/3, and then also put this 3 inside the square. We talked about this before as a square root. So this is really going to become a negative 1/3, the integral of 1 over, and in parentheses now we have x over root 3 plus 1 dx. And now we'll be able to get to our final answer. And so our final answer is going to come from these 3 little mini integrals. Okay, so our first one is going to be 2 ln of the absolute value of x. That's just through definition there. This next one is going to be negative 1/2 ln of absolute value of u, and we'll replace it with what u is equal to in just a moment. And then this third one is negative 1/3 arctan of x over root 3. Okay, so let's just replace that u, and we will be good to go. So 2 ln of x minus 1/2 ln, the absolute value of what x is equal to, which is x squared plus 3. And actually, you know what? Because x squared plus 3 is always going to be positive, we can go ahead and change those absolute value bars to parentheses. So we'll go ahead and do that. And then minus 1/3 tan, or the inverse tan or arctan of x over root 3. So don't forget your plus c on the end, and that should take us to our answer for this type of question. So again, you want to make sure you use those partial fractions that you found before, but then sometimes even when you do that, there's still a little bit of extra work you need to do, whether it's a u substitution or recognizing something special like an arctan. So in this section, we are going to talk about rationalizing substitutions. So this is when you have non-rational functions and you change them into rational functions by means of appropriate substitutions. And when you substitute, you'll have many times things in some sort of root with a function inside, and you'll set that as your u. And this may be effective, and so we'll see an example of that here. This is the last example of this section, so we're almost there. Okay, so as you can see, we do have something of that form. In this case, we have a square root of the function x plus 4. So that is what we're going to set our u equal to. So we're going to have u equal to the square root of x plus 4. And if we square that, we would get x plus 4, right? What's the inside of the square root? And then we can solve that for x. So we'll have that x is equal to u squared minus 4. And so we'll use these pieces to help us replace our integral. We will also need to change this dx in terms of du. So go ahead and take the derivative of x. So the derivative of x is dx. The derivative of u squared minus 4 is 2u du. And since we have all of our pieces now, we can go ahead and try to rewrite this integral. So when we rewrite it, the numerator is going to be our u, because that's what we set equal to u. Our denominator is going to be what we have x equal to, which is u squared minus 4. And our dx is what we have that equal to, which is 2u du. So we need to simplify that a little bit, and that's going to become 2u squared over u squared minus 4 du. Now, if you recall back in the prior sections, when we were talking about ways to deal with rational functions, because now we have a rational function, we have this lovely polynomial on top over a polynomial on the bottom. So we have a rational function. It said, if the degree of px, which is in your numerator, is greater than or equal to the degree of the denominator, you should use long division. So that's what we're going to do here. We're going to use long division to help us deal with this polynomial. Because the degree of our numerator is equal to the degree of our denominator, we are going to use long division. So we are going to take the polynomial on top, which is 2u squared, and make it so that it has a piece for each decreasing exponent, so each term needs to be represented. And then we're going to divide that by u squared plus 0u minus 4. So that's our divisor. And now we're going to do long division. And just the general idea, again, is that you're going to figure out this u squared times what gives me 2u squared. So that would be 2. And then I'll take this 2 and multiply it through the entire divisor. So 2 times u squared is 2u squared. 2 times 0u is 0u. And then 2 times negative 4 is negative 8. So now we're going to subtract like you would in any long division question. The u's, of course, will cancel out. The u squared, will cancel out. 0 minus 0, of course, would cancel out. And then we have 0 minus a negative 8, which is really just a positive 8. So I have a remainder of positive 8. And remember, you always want to write your remainder over top of your divisor. So I'm just going to write that without the 0 term there. So 8 divided by u squared minus 4. So this new expression is the equivalent of what we started with. So 2 plus 8 over u squared minus 4 du. So now we're going to have to deal with this integral. To begin, we're going to need to split them up into two separate integrals. The first one is the integral of 2 du, and the second one would be the integral of 8 over u squared minus 4 du. This first integral there is obviously very simple to take the antiderivative of. However, this second integral, we can't break up into fractions in any way like we did when there were two terms up there. We can't just use a u substitution because if we set our denominator equal to u, we'd need an extra u in this expression in order to get our du term properly. So we can't actually go much further in this particular integral without doing some partial fractions. So we need to factor the denominator. Again, that's kind of our first step there. So u squared minus 4 is equal to u plus 2 and u minus 2. Okay, so we have that, so we have factored, and now we need to make this integral here, this 8 over u squared minus 4, into partial fractions. So what I'm going to do is I'm going to take this integral of 2 du and kind of write that over to the side, and I'll work on like a little mini bubble here, this 8 over u squared minus 4 du integral, to kind of figure out what that's going to be in partial fractions, so that then we'll be able to work this question a little bit. Okay, so we're going to take this 8 over u squared minus 4 and write what it's equivalent to in partial fractions. So we will write this equal to two separate fractions, because we have two separate factors, u plus 2 and u minus 2. And because these are linear factors, our numerators are just going to be constants, 1 degree less. And then we'll take these and multiply through on both sides by the denominator on the left. Now, the denominator on the left, remember, is really just u plus 2, u minus 2 if I were to have factored it, right? So I'm going to multiply through with a u plus 2 and a u minus 2 on the left, and the same on the right, u plus 2, u minus 2 on the right-hand side. So each of the factors would, of course, cancel with the left, leaving us with just 8. And on the right, we would end up with a times u minus 2 plus b times u plus 2. And so what we would want to do is, I think it would probably be easiest if we use the idea of factors here and let let u equal certain values to get zeros in there. So we're using that idea of the shortcut again. So if I let u equal 2, again, we're getting that from the idea of u minus 2 equaling 0. Okay, then we would end up with 8 is equal to a times 2 minus 2, of course, is 0, plus b times 2 plus 2 would be 4. Okay, so this would end up with being 8 is equal to 4b, or that b is equal to 2. Okay. Now looking at the other factor is u plus 2. So in this one, we would want to let u equal negative 2, and that's because u plus 2 would equal 2. So the value of u that we would want to plug in to get 0 would be -2. So on the left, we'll have an 8, and then we would have a, and then -2 minus 2 more is -4, plus b times 0. And so that would give us 8 is equal to -4a. Doesn't look like I have my negative written there, so let me make it a little more obvious. -4a, which would mean that a is equal to -2. Okay, so now that I've done this little side of partial fractions, I can now tell what my integral is going to be set up as. So instead of having the integral of 2 du plus this 8 over u squared minus 4, we'll still have that first part, but now we'll have the two partial fractions as a part of our integral. So it's going to be a, or the integral of a which is -2 over u plus 2 du plus the integral of 2 over u minus 2 du. So notice not only did I write them as two separate fractions, right, but I also wrote them as their own individual integral. Okay, so I'm going to take a moment to clean that up. And all I did was write the coefficients out in front with their signs. So I put that -2 out in front and put a 1, and the +2 in front with a 1 in the numerator as well. So as you can see, each of these is going to require some u substitution. So since we're already using the variable u, we're going to need to pick another variable, maybe the variable v, okay? And we're going to set v equal to our denominator, and the derivative of v in this case would just be 1 du or just du. So we are actually ready to roll on this particular one. So we can actually write this. I'm going to move this -2 out in front. So -2 integral of 1 over u d, or excuse me, 1 over v dv. Okay, so 1 over v dv. So that integral is ready to go. Let's look at this next integral here. This is also going to be a so-called u substitution, but we're going to have to use another variable, so maybe w. So w is equal to u minus 2. So dw is equal to the derivative of that, which is 1 du, or just du. Again, you can move that coefficient out in front. So plus 2 integral of 1 over w dw. And then, of course, we need to remember to bring that front integral, which is a nice simple one, the integral of 2 du down. So now let's write our answers here. So the integral of 2 in terms of u would be 2u. The integral of 1 over v is the ln of the absolute value of v, so minus 2 ln of the absolute value of v. And then the integral of this last one would be +2 ln of the absolute value of w. Now, before you go and replace everything in terms of u, we need to replace these v's and w's first, and then we'll go back one level. So this 2u will still be there. It's just kind of hanging out for a minute. V was the equivalent of u plus 2, so now it's -2 ln of the absolute value of u plus 2. And w was the equivalent of u minus 2, so it would be +2 ln of u minus 2. Okay, so now we have everything in terms of u. Notice we have u here, and u here. So we need to go back up to the very beginning to figure out what we set u equal to. And u is equal to the square root of x plus 4. So all of those u's in our final equation are going to be the square root of x plus 4, because that's what we set it to at the very, very top. So just take a moment to really focus on writing it. So 2 times the square root of x, was it plus 4 or minus 4? For some reason I'm forgetting. It was plus 4. Okay, so let me make that a plus. And then minus 2 ln of the square root of x plus 4, and then a plus 2 outside of that, plus 2 ln of the absolute value of the square root of x plus 4 minus 2. Now, to make this nice and slick, that's what one of my professors used to say, when you want to make things real nice looking, you make them real slick. And so what we can do here is we can actually combine these two ln's. If I were to rewrite the order, maybe it might make it a little more clear. So the positive 2 first, maybe. So positive 2 ln of the absolute value of x plus 4 minus 2, and then minus 2 ln of the absolute value of x plus 4 plus 2. So if I did that, I think it makes it a little more clear that you can combine your ln's, your natural logs, using some of those natural log or logarithmic properties, okay? And so our properties are going to be able to combine these two, and because there's a minus sign here, it's going to be division. So we can say, okay, well, this first part, 2 root x plus 4, that's great. He's just hanging out in front. Plus, and then we can write the ln of, and it would all be 1. It's going to be the square root of x plus 4 minus 2 up top, because that's the positive piece. And then the negative piece goes in the bottom. It's the square root of x plus 4 plus 2. And I'm going to put a squared there. And if you remember, when you have a coefficient of a 2, that little guy can pop back up as an exponent. So he can actually come back here and become a little square. So that's why I'm raising it to the second column. Okay, so that's pretty much as simple as it can get. So the trick on this one, because we had that square root in our original, you really want to look to see if you're able to do some substitution first, and then you may or may not need to do some additional by parts after doing that long division. So this was a pretty involved question because you had to substitute, do long division, and partial fractions in order to get our final answer here.